and it will be given by Nicola Dal Cin, and it's about training nonlinear optical neural networks with scattering backpropagation.
Oh, thanks. Okay. So, good morning, everyone. I'm Nicola. I'm a PhD student with Florian here at MPL, and today I'm going to present some work we've done with him and Clara, in which we propose a method to train on nonlinear optical neural nets. So I will skip the introduction, basically, because everyone here knows that AI is getting more and more energy expensive. But on the other hand, our brains work with 20 watts, so in principle you can do better, and people are trying to somehow change the hardware on which you run these machine learning algorithms. Of course, there are many different research directions in this area. What's particularly interesting for us is how would you change the way you optimize machine learning algorithms when your system is actually a physical system. So let's say you want to do supervised learning. What you would do in an artificial neural net, as you know, is most of the cases you do stochastic gradient descent. So you compute the gradients with automatic differentiation, and you do. In principle, if you have a physical system and you are able to model it, what you could do is to simulate it, do backprof through time, and train it this way, but this is not energy efficient. Also, it's not really reliable because in many cases the digital twin are not very accurate, and that's why some folks have been trying to come up with other methods to measure gradients or approximation via experiments on the system itself. And yeah, the most naive method you could do is just do parameter shift, of course, but this scales poorly with the number of parameters, and that's why there are state of the very good alternatives. There is equilibrium propagation that you know by Chelier and Benjo that works for energy-based model. On the other hand, if you have a lossless system and you have also a time reversal operation, Florian and Victor proposed Hamiltonian echo backprop. And what we were trying to do with this work was to focus on in an intermediate case, which is kind of common. Let's say you have a system which is both driven and dissipating, and how would you find an efficient way to get the gradients out of it? And our main application we had in mind was, of course, optics. From the other hand, why optics? Because you can support efficient linear computation, but also in principle nonlinear dynamics, and these are the two main ingredients for artificial neural networks. So it's kind of natural. So mathematically, what you can think of is, in general, you have an input-output system. You have a set of optical modes. Here A is a vector, and that evolve in time, with this ODE. In a very general way, you can break down the equations by, I don't know, you have a dissipation term, and then you have, let's say, some linear coupling with also the detunings in the diagonal, and then you can drive your system. Furthermore, the important part is that typically you would to have a nonlinearity in your system, of course, and in optics this is kind of tricky. In many cases you don't really know which kind of nonlinearity you have. This can come up from the Hamiltonian or from nonlinear dissipation that you have in your system. So we want it to be very close to experiments and not even require to really be able to model this black box. And how would you define a neuromorphic network out of this? I think the most natural way is just to take your input, the image of a cat and a dog, encode it into the drive that you send it at the green here input node, and then you wait until the system goes to steady state. We assume this happens. And then what you can measure with different decoders in parallel the outgoing light from, you can think about the resonators or cavities, whatever. In particular, you can consider the output at some nodes, the red ones here, to be the output of the network. So let's say if this one is brighter, then it's a cat, otherwise a dog, and etc. So the question is, how would you compute the gradients of a smooth cost function with respect to this y, and also with respect to some physical parameters, which you may think of I don't know, the tunings or the linear coupling between these nodes. Okay, yeah, this kind of model is kind of flexible. It's Hamiltonian system with dissipation and inputs. So it's a port Hamiltonian system, can be used to model microresonators, exciton polarons, and other things. And yeah, furthermore, it was interesting because yeah, it's not an energy-based model, and it's dissipative, so we cannot use EP and HEV. And in principle, we really want to assume like the last amount we can to be close to experiments, so not to be able to engineer or know the nonlinearity and etc. Okay, so I will just skip to how this would work, and of course, you can do like very efficiently with just two experiments, like with the EP and HEB. So in the first phase, you just do the inference, so you encode your input into the drive, you wait until the steady state, and that at the steady state you can measure in parallel with a lot of detectors the outcoming field. So in particular, you know the output from the output nodes, so you can evaluate your cost function. Okay, and this is the first phase. And then what you do is you try to get some information about the gradients. So now your system is at steady state. You keep your green inputs like here clamped. And what you do is that on top of this, you do a linear response experiment. So you inject a perturbation from in the output nodes. And now, of course, you change your dynamical equation, and you're going to measure a different steady state. So some perturbation. And now the trick is that basically you can approximate the gradients with respect to the tunings and the couplings in this case with just difference of quantities that you either inject or measure in the two phases. Okay, so now I don't have luckily for you, I don't have time to go into the details. I just want to give an idea of why this in general is an approximation, especially in optics. And actually, this can be linked to some physical property of your system. So in many cases, if you have a linear system, you also have this nice property, which is reciprocity, namely the system is invariant with respect to swapping the source and the detector. So here, if you inject in J and measure in L, it's the same thing of doing the opposite. Mathematically, of course, if the system is linear, you have the scattering matrix that give you a linear input-output relations, and you can see this property as a symmetry of such a scattering matrix. In particular, Q here is a local symmetry matrix. Actually, can become uglier than this, but we'll keep this formalist because it's easier. For instance, if you have symmetric losses and real couplings, you can pick U to be poly X or poly Y. I mean, the reason why you can choose poly X, it's basically because what this does is exchanges A and A star. So basically, you're doing a local time reversal operation, and that's why this is the case. What happens if your system is nonlinear? Well, now, of course, up to the first order. Okay, I don't know what is happening. It's outside. Sorry. After the first order, you can still expand and get a linear relation from perturbations. And but what happens to the reciprocity? Well, basically, if you have nonlinearity and losses, in our case, you break it because you have all sorts of subphase modulations and these kind of effects. Nevertheless, this kind of reciprocity breaking is is typically much milder than the one you could get in optics, and typically you find yourself in this quasi-reciprocal regime that give you this approximation in the end. Intuitively, why? Well, because what you would like to do is perturb one parameter, see how the state changes, and see how the output changes. What you do instead to be efficient is instead you change the output. But of course, if you don't have reciprocity, this is not exactly the same, but still good enough. So you can. I will kind of go pretty fast on this. You can show, for instance, this more mathematically and also with simulations. Basically, you can prove that the angle between the true gradient and the approximations that you get with this method is linked to the angle between these two matrices. And now, this depends on so many things, like the losses, how you sample your parameters, which kind of nonlinearity you have. Here, for instance, the plots are for the self-care nonlinearity. And what happens is basically that if you do have a steady state, then basically you also have a system which is kind of quasi-reciprocal in the sense that you can train, as you will see. And here in this case, even if you increase the number of nodes, the better the reciprocity becomes. Also, this depends on how you scale your parameters. If you do this mean field, salience, for instance, you can also achieve steady states for higher values of the nonlinearity, and you see that, but still, like the angle is pretty narrow, like especially for gradients. And here, for instance, if you have like even more nonlinearity, so here is all-to-all cross-care nonlinearity. Here, like it's super reciprocal. Okay. I will just show some basic proof of concepts. The first one is on XOR, which is known to be not learnable with a linear function. Here, like you see, this is the mean square error. It decreases like basically monotonically, even if you have like an approximation. And also, like you can learn XOR with just 6 parameters, 3 detunings, 3 couplings, which is better than you would like with the multi-layer perceptron. Okay. Okay, this is just a slide to show like how the gradient approximation works during training. So this is the angle between these two. Like actually, it's the cosine similarity. So one is good between these two matrices. This instead is the cosine similarity between the true and the approximated gradient. And you see that basically this is super good. And here kind of degrades, but the gradient is 0 there. So that's why. Okay. The final example I'm showing, actually just I wanted to point out that in the end, like if you do want to go to experiments, you have noise and etc. So like the effect of noise in principle is much worse than this. Like I don't have time to show you the simulation with noise, but like yeah, trust me. So final experiment is the traditional MNIST dataset, and here the connectivity is kind of sparse, inspired by convolutional neural nets. And what we get is basically something much like very comparable to a similar size convolutional neural nets. We average the gradients over mini batches of size 10. This is the training accuracy and the test accuracy. And you see that basically in the ablation casing, we do not have the nonlinearity. We reach like somehow like 92.5%, I don't know. And then like as soon as you increase the nonlinearity, you unlock the nonlinear expressivity. So this actually like helps. Okay, so like I will basically skip the summary. I'll also will leave you with the paper and some related work. This can be actually some things that I don't have time to say. Like this can be seen as a generalization of the generalization of equilibrium propagation for vector fields, but it's actually needed to extend to this kind of system. And also like other works appeared later, so I couldn't cite them in my preprint, but they also like do something similar. They assume some more stuff. So of course, yeah. But thank you for your attention.
Yes.
Thank you. That's very interesting.
Thanks.
I have very basic question to ask. In your coupling matrix J, I know the general case is complex valued, but you specifically commented on its being real.
Yeah, here is
so
real.
My question is, why do you put it in conservative part? Like conservative or reactive or Josephson or unitary, depending on the field you're not in dissipative part. Because for instance, for minimization purposes, we have to put J in the dissipative part of the equation. Otherwise...
Like, I mean, the reason, like, you mean like why there is like a minus I in the equation, basically? Yeah. I mean, this comes from, yeah, sorry. I mean, oops. Yeah, but I mean, like if you write basically the Hamiltonian version, like this is a Porter-Hamiltonian system. So you have like, this are basically the Hamilton equations. So this is the linear part, and this is the nonlinear part. And this is the dissipation, which is linear in this case. And when you change your basis, basically you get like this minus I and etc. The reason why with real is better is because like you don't have like this hopping like with this squeezed term like in the Hamiltonian. So like in that case, there's like I think the symmetry matrix would be more complicated and it's uglier. But yeah, like the reason is just because like this come from the Hamiltonian equations for yeah. But maybe I didn't understand well your question, so maybe we can discuss later. I don't know.
Thanks a lot for the great talk.
Yeah.
So you showed us the effect of adding in noise. Do you have any comment on how the size of your nudge affects the sensitivity to noise?
Yeah, that's a very good question. So in principle, if you do have noise, like things gets like uglier because like you have like a Langevin equation and let's say you have like white noise. So here, like even like what is a steady state, like you could argue you have an average distribution, and what you can measure is actually just an estimator of this. So like you can measure. I think experimentally this is reasonable. You measure your output for a while, and then you average out the noise, and this actually affects a lot of here you have to do another expansion. It's a bit more complicated because it's a stochastic nonlinear differential equation. So but if you do your math, basically you show that your gradients still has like the approximation of the quasi-reciprocity bias, and actually noise affects this bias. And then you add another bias, which is given by like how noise affects the correlations, and then vice versa, because this is nonlinear. Like this is more complicated. And you can show that if you increase this averaging time, like the loss gets better and better. And coming to your question, of course, like you're saying, I'm a steady state. I want to inject a perturbation, and this perturbation is gonna fight with the noise in order to signal to noise ratio, etc. Well, like here I've done like some numerical experiments and etc. And here basically we were like just studying how the nudging size behaves compared to the nonlinearity, and also this depends on how much you're time averaging and the noise and etc. And you get like what you would expect. Like if your nudging is super small, then you kind of like have some bad performances because the noise affects you, but you have like a big like intermediate regime in which you can do like your nudging and still works. And also like this depends on so many things, like even on on T, like if you sample for more time, this works better. Even if you pump like more photons, like this works even better. But okay, yeah. So.
All right, let's thank the speaker again.